class, welcome back to thermodynamics. In this lecture, we are going to be we're going to be applying the second law, so entropy, to control volume problems. And specifically today, we're going to be studying isentropic processes. And so with an isentropic process with control volumes, that means that the change in entropy with time is zero. So remember, with control volumes, we are dealing with mass flows. So we're dealing with rates. So instead of energy, we're looking at energy per time. We're looking at power. So I just wanted to go back and review with you some of these different components that we've been looking at as control volumes. So let's begin with nozzles and diffusers. And we're also going to talk about some of the assumptions that are built in. So remember, with a nozzle, we're looking at a liquid. And it's going to be, the liquid is going through some greater cross-sectional area opening to a smaller area exit. And what we're getting with a nozzle, for example, is we're speeding up the velocity of a liquid. So with nozzles and diffusers, we're either speeding up or slowing down a fluid. That's the goal. And with a diffuser, for example, if we look at a gas, so this would be a liquid. With the diffuser, we're typically dealing with a gas. And we're sending it through a smaller area opening to a larger cross-sectional area exit. And so we're slowing down the gas. And so some of these assumptions that we build into our models are that Q dot is zero. We're not getting any energy transfer with time between the nozzle and its surroundings, or the diffuser and its surroundings. We don't have any power that we're putting into the system that we're getting out of the system. We're dealing with the steady state problem. So dt is zero. And also that the change in kinetic energy is not zero, right? Because we're changing velocities at the inlet and outlet. So with nozzles, we're increasing velocity. With diffusers, we're decreasing velocity. So there's definitely some change in kinetic energy. But the change in potential energy is zero because we're not getting any significant difference in elevation between the inlet and the exit. And so next lecture, we're going to be learning about isentropic efficiencies, but I just want to briefly introduce the efficiency of a nozzle here, the isentropic efficiency of a nozzle, just so that you see it once before we look at it a little closer next lecture. So remember, our symbol for efficiency is the Greek letter eta. That looks like this elongated N. For a nozzle, it's going to be equal to the outlet speed, so V2 squared, divided by V2 S squared, which is also the same as the ratio of KE, kinetic energy at the exit, and I think I've been calling this EK. Let's be consistent. So kinetic energy at the outlet divided by EK2S. Okay, so what is this mysterious S thing? All right, so the idea is with efficiency, we're looking at a fraction, some proportion from 0 to 1 or from 0 to 100%. So it's going to be real over ideal is what we're comparing. And so the real outlet velocity, the actual observed outlet velocity, compared to what the outlet velocity would be for an isentropic process. So if our change in entropy were 0, what would that velocity look like? Because we're going to lose some speed, some kinetic energy to entropy production. And so remember that kinetic energy is equal to 1/2 mv squared, which is where this ratio of the mass is going to be the same, and the 1/2s will cancel. So that's why we can get the efficiency just by looking at the ratio between the outlet velocity squared compared to the outlet velocity if we had an isentropic process. And the other thing I want to say is that typically when modeling this, we typically model that our entropy production is 0. But we will be having more practice with these sorts of problems in the upcoming weeks for the rest of the semester. All right, now valves. Let's look at valves. And the goal of a valve is to drop pressure. Typically. So with a valve, draw it with a little X here, have our inlet, have our outlet, and we have some fluid flowing. And our modeling assumptions here are that heat transfer is 0, power is 0, we don't have any power used or produced, that our entropy production is going to be greater than 0, and we're going to be operating at steady state, and our change in kinetic energy is going to be 0, and our change in potential energy is going to be 0. All right, so that's a valve. And let's move on to turbines. We use turbines a lot in power plant design, and we'll get more into power plant design in the upcoming lectures as well. And so the purpose of a turbine is to get or produce power. So looking at a turbine, we're going to have usually some vapor going in and turning the turbine so we get work out. And so clearly built into our assumptions, of course, is that W dot is going to be greater than 0. That's the whole purpose of a turbine. Typically, unless it seems otherwise, our heat transfer is going to be 0. And this is ideal. And if it's not ideal, then yeah, we might get some heat transfer going on. That's for an ideal situation. And typically our entropy production is 0. And that's also for an ideal situation. Okay, so they might not be 0. But unless you're told otherwise, typically you can assume ideal. And we'll go through some more examples of that in the upcoming classes. And we're assuming steady state. So d dt is 0. Delta KE is 0, typically, except there's an exception to that, really just except for jet engines, where you're going to get a huge difference in velocity at the inlet and outlet. So except for jet engines, or unless you're told there's some difference between inlet and outlet velocity. Okay, and then lastly, the change in potential energy is 0. All right, and so the goal of a turbine is to get power. Let's just briefly look at the isentropic efficiency then of a turbine. So that's going to be eta sub T is going to be equal to our work out for the control volume divided by m dot compared to the work out for the control volume over m dot for an isentropic process. That's what that S is. And so this is going to be equal to H1 minus H2 divided by H1 minus H2S. And that H2S is where delta S is 0. Okay, so we have the same inlet conditions, these H1 enthalpies, which are function of temperature typically. And then we have a different H2S, and that's if we assume that there's no change in entropy. So for an isentropic process, and that gives us our efficiency for a turbine, our isentropic efficiency. Now looking at heat exchangers, it's pretty obvious what their goal is, right? And that is to exchange heat. But if we look at a heat exchanger, we have some higher temperature line, some lower temperature line. We have a mass flowing in this way and mass flowing in this way. They don't have to be the same masses. They can be different substances, and you're going to get some heat exchange between the two lines, but not between this entire system and the surroundings. So the built-in assumptions for a heat exchanger are that Q dot is 0, W dot is 0, entropy production is positive. We're working at steady state. Change in kinetic energy is 0, and change in potential energy is 0. All right, and then lastly, for cycles in general, the sum of heat transfer, the rate of heat transfer, is equal to the sum of energy transfer or power. Okay, so those equal in cycles. All right, let's move on to talking briefly about ideal gases in isentropic processes. Then we'll do a couple exercises together. Okay, so remember, isentropic process means the change in entropy, the rate of entropy change for the process is 0. So rate in entropy, so ds over dt is 0. Okay, so no change in entropy over time for an isentropic process. And so for an isentropic process where we have an ideal gas as our working fluid, we have some simplifying equations we can use. And so those are that the ratio of T2 over T1. So remember, These T's are absolute temperature scales, so either Kelvin or degrees Rankine, is equal to the ratio of P2 over P1 to the K minus 1 over K. And that's going to be equal to the specific volume ratio, V1 over V2, raised to the power of K minus 1, where you're given some constant K for the process. Okay, so remember, typically we have this constant that is associated with ideal gases. And for example, Cp is defined as this constant Kr over K minus 1. So whenever you're given that we have an ideal gas undergoing an isentropic process with K equals some value between 0 and 1, then you can apply these ratios, okay, between state 1 and state 2 of that process. So we're going to try this in a couple exercises. So beginning with air at 500 kilopascals, this is number 6.101 from your book, at 500 Kelvin and a mass flow of 600 kilograms per hour, enters a pipe passing overhead in a factory space. At the pipe exit, the pressure and temperature of the air are 475 kilopascals and 450 Kelvin, respectively. Air can be modeled as an ideal gas with K equal to 1.39. Kinetic and potential energy effects can be ignored. Determine at steady state A, the rate of heat transfer in kilowatts for a control volume comprising the pipe and its contents, and B, the rate of entropy production in kilowatts per Kelvin for an enlarged control volume that includes the pipe and enough of its surroundings that heat transfer occurs at the ambient temperature 300 Kelvin. And it's occurring to me that I think I might have said K is between 0 and 1. K doesn't have to be between 0 and 1. It's a positive value though. Okay, so let's draw our model. So we have a pipe overhead. We have air flowing in it. The mass flow rate is 600 kilograms per hour. And we're given that K is equal to 1.39. We're given P1 is 500 kilopascals. We're given T1 is 500 Kelvin. We're given P2 is 475 kilopascals. And we're given T2 is 450 Kelvin. All right. And so first, we want to find the rate of heat transfer in kilowatts. So we're going to find Q dot, and B, the rate of entropy production. And B, we're looking for sigma dot, the rate of entropy production. So for A, let's start with our energy balance. And so Q dot minus W dot is equal to M dot. And so remember now, with control volumes, we're not just dealing with differences in temperature, but we also have, because we have a fluid flowing, we're going to have pressure volume work as well. And so built into that for control volume problems, we need to use enthalpy. Remember, enthalpy is U plus P dV. So we're going to have H2 minus H1. And so we could also write this as, so remember, H, delta H is equal to, M delta H is equal to MCP delta T. So this is equal to MCP T2 minus T1. And with ideal gases, CP does not equal CV necessarily. And that we can find CP. So CP is equal to K times the gas constant for air divided by K minus 1. And so this is going to be 1.39 times 0.287 kilojoules per kilograms Kelvin divided by 0.39. Okay, K minus 1. And so now let's plug this in. And if we are looking for Q dot is going to be, oh, one more thing. Okay, we're just having air moving through a pipe. We don't have any work in or out, any power in or out. So Q dot is going to be M dot CP times T2 minus T1. And so M dot was 600 kilograms per hour. And we have to put this in base metric units, so we need to convert hours to seconds. So 1 hour is 3,600 seconds. And then our CP is 1.0229 kilojoules per kilogram Kelvin. And lastly, our delta T is going to be T2, which is 450K minus 500K, so minus 50K. And this gives us a Q dot of minus 8.524 kilowatts, because we have kilojoules per seconds left. And a kilowatt is a kilojoule per second. Okay, so that was part A. Let's look at part B. So for part B, we are looking for the entropy production, the rate of entropy production. And so in this process, okay, we're dealing with, oops, sorry. So we're dealing in steady state. So delta S is equal to Q dot over TB. Okay, and we just do it going from inlet to outlet plus the rate of entropy production. And so if we wanted to solve for entropy production rate, that is going to be equal to, well, the delta S can be written as M dot times CP times the natural log of T2 over T1 minus R times the natural log of P2 over P1 minus Q dot over TB. All right, so let's break this down a little bit here. So as far as, so this is a process with constant specific heat, as we found in the first part with Cp equal to 1.0229 kilojoules per kilogram Kelvin. And so when you're looking for delta S for an ideal gas with a constant Cp, you can do this little trick where delta S is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And that's just because we have an ideal gas. So this is delta S for an ideal gas where Cp is a constant. And that would be equation 6.22 from your book, if you wanted to look at it. Okay, let me get my notes, which I threw on the floor. Okay, now, where was I? All right, so we're looking for the entropy production. And we got Q dot in part A. We are given TB. Our ambient temperature is TB. That's 300 Kelvin. And so I think we have everything we need. All right, so let's plug everything in. So the entropy production rate is going to equal our M dot, which was our 600 kilograms per hour times 1 hour to 3,600 seconds times our Cp, which was 1.0, where did it go? Yeah, 1.0229 kilojoules per kilogram Kelvin. And then we have the natural log of T2 over T1 T2 over T1, and that would be 450 over 500 minus R, which is 0.287 kilojoules per kilogram Kelvin times the natural log of P2 over P1, which was 475 over 500. And then we're going to subtract off Q dot. So our Q dot we found in part A was minus 8.524. So we're going to add 8.524. And we're going to divide by our boundary temperature, which I want to say 300 Kelvin, but I got to look again. Yes, 300 Kelvin. All right. And this was in kilowatts. Okay, and so this will give us a rate of entropy production that is 0.0129 kilowatts per Kelvin. Okay, that's it for that one. Now let's try one more. And if you're feeling really good and you want to pause it and try this on your own, you're always welcome to do so. Okay, air in a piston cylinder assembly is compressed isentropically from state 1, where the temperature is 35 degrees Celsius, to state 2, where the specific volume is 1 tenth of the specific volume at state 1. Applying the ideal gas model with K equals 1.4, determine A, T2 in degrees Celsius, and the work in kilojoules per kilogram. So let's draw a little sketch. We have air in a piston cylinder assembly. So here's my air in my piston cylinder assembly. And we have T1 is 35 degrees Celsius, and V2 is equal to 0.1 V1, since it's 1/10, and our K is 1.4. Okay, so we're tasked with finding the following. T2 and B, this work. All right. So for part A, to find T2, let's use our relations for ideal gases undergoing isentropic processes. So if we look back at these relations, we see that T2 over T1 is equal to P2 over P1 to the K to the minus 1, K minus 1 over K, and that's equal to V1 over V2 to the K minus 1. So we can use T2 over T1 is equal to V1 over V2 to the K minus 1. So let's do T2 is equal to T1 then times V1 over V2 to the K minus 1. And then we're given T1 and we know our ratio between V1 and V2 and we know K. So T2 is going to equal T1, and the trick here now is we were given T1 in degrees Celsius, but in order to use these relations here, we have to deal in absolute temperatures. So T1 is going to be 308 Kelvin, so 35 plus 273, and then we're going to multiply by V1 over V2, and so it's going to be V1 over 0.1 V2, which gives us 10 because the V's cancel, or V1 over 0.1 V1, and the V1's canceled, we end up with 10 to the power of 1.4 minus 1, which is 0.4, which is going to give us 774 Kelvin. And it asked for T2 in degrees Celsius, so we just have to subtract off 273, and so that's going to be 501 degrees Celsius. All right, now for part B, I'm just going to open up a fresh sheet. So for part B, we're looking for work. And so we're not given a mass here, and we're looking for work on a mass basis anyway. And so we're dealing with our little q, if we're doing an energy balance, minus W is equal to, and so now this is not a control volume problem. This is a control mass problem. We have a constant mass, our volume's changing, and so we don't have a flow rate. We're not dealing with rates. We're dealing with energy units again. So not per time. And so it's going to be Q minus W, and we're not going to get a change in kinetic energy. We're not going to get a change in potential energy. And so it's just going to be Q minus W is equal to delta U, or U2 minus U1. All right, so remember that to get delta H, we can do Cp delta T. To get delta U, we use Cv delta T. And so this is going to be equal to Cv times T2 minus T1. All right, and for this problem, our heat transfer is going to be 0, dealing with an isentropic process. So we're not gonna have heat transfer, and so then we just need to find Cv. So Cv, by definition, is equal to the gas constant, R, divided by K minus 1. And this is going to be equal to 0.287 kilojoules per kilogram Kelvin. Divided by 1.4 minus 1 is 0.4. And this is going to give us a Cv of 0.7175 kilojoules per kilogram Kelvin. And then finally, we can solve for W. And so W is going to equal Cv T1 minus T2. I just distributed the negative sign throughout. And so it's going to be equal to 0.7175 kilojoules per kilogram Kelvin times T1, which was 35 degrees Celsius, and T2 was 501 degrees Celsius. And the reason, remember, I can write down the temperatures here in Celsius rather than Kelvin is that we're looking at a difference, and a difference is in Kelvin is equal to a difference in degrees Celsius, so that's okay there. And what we end up with is work is equal to minus 333.6 kilojoules per kilogram. Okay, well, that's all for today's lecture, and I will see you next time when we look at isentropic efficiencies.